We will set you up on camera. Right.
Who's the Disney cameraman? Should we start? Yeah. Okay. So it's my pleasure to introduce Ruta Mehta. So Ruta is a faculty at in the CS department at the University of Illinois Urbana-Champaign. Before that, she's been a postdoc at Georgia Tech at Science. And even before that, she was a PhD student a little ways away at IIT Bombay. So Ruta works in various fields. She's been responsible for some absolutely seminal contributions in game theory, including computation of equilibria, complexity of equilibria, pair division, and so on. She received numerous awards for her work, including the Essay and Doctoral Dissertation Award, the NSF Career Award, and many others. She is practically a Bombayite. She's did a PhD from IIT Bombay. She did a master's before that from IIT Bombay. But she's coming here after a long time, so I'm happy to have her.
Really happy to be here, and thank you for a kind introduction. I have done some work, but okay, so I'm trying to get rid of this panel. If I can.
The Zoom panel?
Yeah. There is one, yeah, okay, it's gone. Okay, I think it should be okay. Okay. So this is I want to talk to you about again equilibrium computation. That is really a problem with close to my heart. I started working on that during my PhD, and so that was mainly for goods. Now I've switched to chores. I realized after having a baby and get married that chores are so important to be divided properly. So better work on it and understand what should be a solution that does not lead to a divorce. So the joint work with Shant Budagian, Bhaskar A. Chaudhary, Jewel Garg, Christian Berger, Peter McLaren, and Tian Long. Out of these, Shant was my student, Bhaskar is a professor, Jewel is a professor at UMC, both of them. Christian is of Columbia, Peter was a Jewel student, and Tian Long is a Christian student. Why so many authors? Because the talk is a combination of the four papers. And why am I giving this talk? Because there is one problem open that I've been struggling with since last 5 years. We have made some progress, haven't solved it yet. So what better audience can be at to show you how to solve this? Okay, so one slide or two slide motivation. Chores are as important as goods, even in the market setting, like TaskRabbit or even Uber can be thought of as a chores market where drivers are doing chores to earn. So basically, we are in the setting of dividing items. These are divisible items. You can think of as time, bread, milk, hours of teaching, hours of doing housework, and so on. And you want to divide them among a bunch of people, and you want to find fair and efficient allocation. Really, that is the main motivation where I started. Now, many applications, not going to go too deep into this, but a school seats assignment, air traffic control when there are climate the weather issues for the flights, kidney exchange, vaccine distributions, and so on, or dividing assets and liabilities when you are dissolving a company, or dividing budgets or duties among different wings of defense. So in general, we have n agents, m items, all divisible. Agents, we generally assume that have concave valuation. Concave captures decreasing marginal returns. If I give you one ice cream, you are happy, I'm very happy, probably. I give second, maybe little more happy, but not as much as the first. The extra utility is not as much as the first one. So the extra utility keeps decreasing. So concave. And finally, so you're going to reduce the problem to finding a competitive equilibrium. So why competitive equilibrium? And I will tell you in a bit how the competitive equilibrium is going to give us nice properties. Okay. So what is a competitive equilibrium? In the traditional goods setting, there are a set of agents who have money to buy stuff, and there are goods in the market. Given prices, they will decide what they like the best among, or what can they buy that maximizes their utility, subject to whatever money they can spend, right? So they basically will try to buy a bundle that maximizes their utility. Should I not be moving too much?
No, it's fine. It's fine. Don't worry about it. Yes. I mean,
No worry.
yeah.
Okay.
Those on YouTube should come here.
Buy optimal bundle, or I will try to stand here. That will generate demand. And we say that these prices are at equilibrium. So once you know the demand for every agent, we know the aggregate demand for every item. Right? You say I want 1 unit of milk, I say 10 units of milk, and total is 11 units of milk in demand. If the supply is also 11 units, then we say that demand equals supply and price are at equilibrium. And specifically for fairness sake, we'll be looking at competitive equilibrium with equal income, where all of us have the same amount of money to spend. There's some kind of a equality or fairness criteria.
And the price of the goods is same for all the agents?
Yeah, so we all see the same price. You see $10 for milk, I also see $10. So, okay, so first of all, this has to be NV-free. Do you see by NV-free in the sense that I'm going to buy some bundle with $1, you're going to buy some bundle with your $1. You will not say that you like my bundle, or I will not say that I like your bundle more than mine. Why is that?
To solve $1.
Because we both have $1. If you like mine, why didn't you buy mine? Right? So it's NV-free, right? Using NV-freeness and the fact that demand equals supply, we can also show that it's proportional. What is proportionality? Proportionality says that every agent should get at least 1/n of the value she has for all the items in the system. Okay. Why 1/n? Because there are n agents, and this is called a fair share in the fair division literature, because for an agents from my perspective, I don't know what you like. I know what I like. It might be the case that you like exactly what I like. Then all of us can't get more than 1/n of the fraction of the value, right? The value is going to be divided equally. So that's why it's important. And finally, first welfare theorem from economics says that the allocation is Pareto optimal, meaning that there is no other allocation that achieves where no agent is worse off, at least one of them is better off. So it's on the Pareto optimal frontier.
So the fact that proportional also depends on the fact that the value functions are concave.
Yes. Yeah. I'm using concavity everywhere. If you go outside concavity, not everything would follow. And finally, it also maximizes something called Nash welfare. So social welfare is sum of the values of all the inputs. Yeah. But I kind of want to argue that that's not a very good notion for fairness or efficiency. Why? Because whatever be the fairness notion, it should be scale invariant. If I measure my happiness in dollars, or I measure in rupees, or I measure in euros, that should not matter. The outcome should not change, right? But if I'm saying that I'm going to maximize welfare, social welfare, which is sum of the value, then I'll try to give the items to the agent who values them the most. Right? So if you say that you like milk at 100, I say I like milk at 10, I'll give the milk to you. But maybe you are saying 10 in rupees and maybe I'm saying 10 in dollars. So what I'm saying is that typically in economics or in this social choice theory literature, scale invariance is a very, very important property. And Nash welfare is maximizing the product of the values, not the sum of the values.
So here you're assuming, I missed it, that every agent has the same budget.
Yes.
Buying power is the same.
Buying power is the same, but the values might be different. It might be that you like milk, I like cheese.
So that's really unrealistic. Buying power, but this is what it is.
For now. Yeah. Yeah. For fairness sake. But the market would make sense even without that assumption.
So which part is unrealistic?
That we all have the same buying power. When I value something as $10, at 10 cents. Yeah, if my buying power is $1, and if somebody else's buying power is, then it's not the same thing, no? I mean, then giving, I mean, then you have to scale it down everybody's budget to the same thing.
Okay, buying power is not the same thing as a budget, is it? I mean, like,
Like, buying power means like whatever money I have to spend.
Yeah,
That would be different.
so
for different people.
we all have $1 in our pocket. We all go to the market and to buy stuff that we like.
That is the one I'm saying is a little unrealistic.
Unrealistic in the market sense, but not in the fairness or fair division sense. So people use the notion of, so typically I'll tell you that, okay, I want to divide, let's say,
Simply because not everybody has the same buying power.
no, I
Yeah,
agree, but.
yeah.
I mean,
So I'm going to apply that to a scenario where you can't involve money. So let's say you want to divide office supplies among the faculty and the students. Okay, how are you going to do that? You can't charge them money.
No, but then people can value the same good differently. Right?
Yeah,
So
exactly.
But then we also assume that the price of 1 liter of milk is same for everyone.
Sure. But you have $1, I have $1. If I tell you that this is of 50 cents, now we have to decide, is it worth 50 cents for you to buy out of your $1? We both have to decide.
If one person is say thrice the buying power as an average person, you can say there are 3 copies of the same person and.
You can do that, yeah. I mean, so it's also you can do these scalings and what, yeah, you can do these scalings. I'm kind of trying to show you good properties of competitive equilibrium, which goes outside of the market realm. You can apply this outside of the market questions. Does that make sense? You can extend all of these things to non-equal budgets. Okay, and everything will work. Even the algorithm would work. Okay. But I'm trying to show you because from the social choice theory perspective that which has nothing to do with market or competitive equilibrium, still it is useful.
The Pareto would work even if people have different budgets, right?
Definitely, yes. This would work. This would work up to a weighted version of this. Yeah, and that will also be weighted version. Everything will work. Okay.
Within the approximate NVIDIA.
Not approximate, weighted NVIDIA. You have $2, I have $1. Definitely you can buy more than me. Right? So I will envy you. But if I halve your items, then I will not envy you.
So this is all divisible, right? So the approximate is.
Half the items, so the value is a market value.
Half your bundle I will not envy because I anyway have half money, so I can't buy. Yeah. Long history, as you can imagine, bread and butter of economics, right? So, and lots of Nobel Prizes. So not go into that. Computer science started looking into it in 1990s, I think. Academic was the first one, I think. If I, as far as I know. But our question, so the previously economists asked for properties of equilibria, existence of equilibria in different settings. This was a very stylized market. You can have firms, blah, 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 taxations, this and that. And they were mainly concerned about existence and properties of equilibria. Computer science immediately started asking, can we compute these? And there were convex programs when the valuations functions are homogeneous, and there are quite a few. There are polynomial time algorithms when valuation functions are linear. A lot of work, simplex-like algorithm. I have also done some work in this area. Some of the M's are Mehta, XV. And a lot of people have worked, like it's long, but all of these works are for goods. Okay. So what about chores?
Sorry, silly question. So what is given and what are we computing?
We are
What's the computation's question?
Good. So the question, the given is, let's say budgets, if you want the budgets not to be equal, and the valuation functions of the agents.
How do you price it?
And we want to compute the prices.
You want to price it, you want to find the price and allocation, that is computability. In the sense that when given the price, every agent will tell you what bundle they like the most, given subject to their budget constraint. When you aggregate the demand, even these demands, you aggregate the demand for all the goods, demand should be equal supply. In economics class, you may have seen these curves, right? demand, supply curve, wherever it is.
All the economic classes you've taken.
Or somewhere in the news, somewhere. So this is the price and this is X. As you increase the price, the supply is going to increase because more supplier will be happy to supply at these higher prices.
So budget of every agent is given and
So the budget
The
is.
valuation function,
and the
valuation
valuation function is something that associates a number to every
but every bundle. Yeah, so
bundle.
the valuation function,
MITs.
so
Given a priority for each item.
yeah, so for agent I, the valuation function can be written as,
Right.
let's say, assuming the supply is 1, it is without loss of generality. Given an n-dimensional vector, it gives you, I don't know if you can see,
Yeah, like that, yeah.
and it's a concave function.
And then we would like to find prices of the goods satisfying a bunch of properties, namely supply equals demand.
Yes.
For every one of them, everybody is happy.
Yes.
How are you?
So the valuation function is always given for a bundle, right? It's not for individual items.
I mean, individual items may not be enough to figure out what.
You can ask for, let's say, 0.5, 0, 0, 0, 0. I mean, you can always restrict your function to one dimension and you'll get a function for one individual item.
And how is this given as an oracle?
Let's say order. But I'm going to simplify a lot because we are stuck at a very, very simple case of linear. Okay, and then everything will be very explicit. The input will be completely explicit. Okay.
Right, so just to recap, so we assume that the supply for every item is unit.
Yes,
Budget
supply.
for everybody is unit.
Yes.
So the only relevant inputs are the valuation function for each agent.
Yes.
And now we have to find out prices and optimal bundles for each agent.
Yes.
That's all.
Just to simplify our lives. Okay, so what about chores? Would you pay to buy chores?
One question here.
Yeah.
Why is it clear that such a solution even exists?
Very good question. Economists proved that it does through fixed point theorem, but it is not at all obvious that it exists.
Thank you.
And I'll show you for the problem that we really want to handle, how we can kind of reduce that. So definitely for chores, you're not going to be paying for buying chores or consuming chores.
Just curious, what is this theorem for in economics?
Additive proves the existence.
I don't know.
Yeah. And this was one of the results for which they got the number.
Yes.
It was based on Nash's result, but. So now you have to get paid for doing chores. So of course, we get paid for teaching, we get paid for doing jargon, we get paid for, yeah. Sorry? So I hope it's okay to use some Indian words.
No, so here is concavity and reasonable assumption at all? I'm just right.
Let's see.
Okay.
Let's see. Yeah, good question. Is concavity reasonable assumption for chores? So okay, so let me first define. So now the negative payment, negative price meaning if you do these chores, you consume these chores, you get paid for it. And you have every agent has an earning requirement. Okay. So once you set up that, okay, this chore is going to be paid $25 per, right, per unit, $5 per unit, $20 per unit. Each of you have some earning requirement. Okay. And so you will demand your minimum disunity bundle subject to the earning constraint. So exactly the same, but the money flow reversed. That's it. Okay. But now you are minimizing the pace, the disunity. Okay. Or you can also think of it as maximizing negative utility. You can think of disunity as a negative utility and then you are maximizing it. which is the same as millimetric. Again, same formula equilibrium is demand equals supply. And we are again going to ask for CEI, which is equal income. And now you can think there's a obvious application, household chores. How do you divide chores among the people in the family? You can't ask them money for doing jaro, but or pay them.
So this also exists.
Good. With a caveat. Yes. So, and then you can, in the most general case, you can have mixed chores, goods, and you can ask the same question. Now, defining CEI is a bit tricky here because so in the previous case, in the goods case, you have $1 to spend. In chores case, you have $1 to earn. When you have goods and chores both, should it be $1 to spend or $1 to earn? So you have to specify, given the instance, whether it's a chores heavy instance or a goods heavy instance, and accordingly you give like plus or minus one budget. But yeah, I want to show you that we can do everything about mix if we can do chores properly. So let's focus on, first let me tell you what is known for the most general mixed case. So Bogomolya, Mola, Sardimarsky, and Janosky, until like 2017, this question was not very asked or well understood. They said that if VIs are one homogeneous, I'll tell you what one homogeneous is. So this is the class of concave. Then one homogeneous is a subclass where it just says that if you have a bundle and you multiply it with a scalar, let's say you halve the bundle, then your utility halves. Your utility just gets multiplied with the same scale. That's one homogeneous function. Okay. And many interesting class of functions lie in there. And what I am interested in is linear, the simplest. Okay, so for this, they gave a nice CI characterization, but they showed that even for the linear valuations, the CI set can be non-convex. Now, let me just recall that for goods, I mentioned quickly though, that for the linear case, there are strongly polynomial time algorithms, there are convex programs, and so on. So for goods case, when the valuation functions are linear, everything is very nice. A convex set, there are many convex programs for characterizing, for capturing the equilibria. There are strongly convex programs, strongly polynomial time algorithms for finding equilibrium and so on. For chores, even for linear, the set is highly non-convex. And for this reason, they kind of expected that there might be computational difficulty. I had spoken with Mola, who is a famous economist, that they tried to come up with a nice formulation and some algorithm, and they kind of failed, and that's why they put this quote in that paper.
So what's a good example of one homogeneous that is not linear?
Max.
P naught. P naught. LP naught. Max also. And max is a extreme case of. So for linear valuations, when number of items or agents are constant, then there are polynomial time algorithms. But general was open, and this is generally some kind of a nice counting argument. So you say that the equilibria can have to follow some configuration. If number of agents or number of items is constant, these configurations are polynomial. You check every configuration and that's it. Okay.
What is MANNM?
No. Mixed mana. Oh, thank you. Mana meaning item set. In the literature, it's called sometimes also called mana. Mana meaning item set. An item set that has more mixed items. Question was, what's the final complexity with the linear valuations? Is it really hard? We initially suspected it might be hard, but then failed to prove it. So then we tried, let's try approximation algorithm. Instead of directly going for exact, we are not anyway able to get an exact algorithm. So what we could show, the first result was a counterintuitive algorithm, which is kind of a continuous method, but it works from the exterior of some feasible region. So we called it exterior point method. But it gives us only approximate solutions. It extends to general non-homogeneous functions and to mixed manner. And I want to tell you about that particular algorithmic technique because I think that's a new way to looking at the problem or looking at this kind of problem. And I'm hoping that it may find other applications. And then in the follow-up work, we could also give a combinatorial algorithm because so all of these are for linear valuations, okay? And so, yeah, I'm saying linear valuations. So I'm going to define the problem in a brief, but in a minute, but I just wanted to tell you the results that I want to talk about. And finally, very recently, we could come up with some nice convex programming formulations with nice properties and that give us still an FPTASs, but one of the best so far. So I want to tell you about these two right now. So let's get started. Again, just recall n is the number of agents, each has, and I'm going to focus on beds and not mix because mix makes everything very complicated. So, and the main crux of the complexity comes from beds. So let me just focus on the beds in chores case. So n is going to be set of m divisible chores and supply of every chore is 1. This is without loss of generality. And the valuations I'm going to assume to be linear. So here, because these are chores, and when we talk about the value is going to be negative, right? And keeping track of negative numbers is going to be hard. So I'm going to switch and say that this utility is the mod of that value, the absolute value of Vij, and now di of xi is this utility function. Instead of maximizing the value, I'm going to minimize the utility. This so far so good. The notation is fine. Yeah. Okay. So what is CEEI? So again, there'll be prices. These are the payments now per unit of chore done. P1 is the payment for chore 1 per unit done. Yeah. Once I announce these prices, every agent is going to do this calculation. She will say, I need to earn $1. Yeah. Okay, look at all the bundles such that I earn $1. That's a dot product of price and the amount. Yeah. Give me the one that minimizes my dispute. Yeah. Dij is the disutility of agent I for chore j. Xj is the amount of chore j that she's demanding. So if she demands xj, she gets dij times xj disutility because this is linear. Sum or all j, all the chores, this is the total disutility she gets. Right? And she gets paid pj times xj. Pj is the per unit payment. If she does xj amount, she gets pj times xj money. Right? And sum over all j, that's a dot product of p and x vector. That should be at least 1. Subject to that, minimize the disutility. Right? And if you stare at it a bit, this is an LP. Right? You will see.
Xi are all greater or equal to 0. No?
Right?
Xi are all greater or equal to 0.
Yes, thank you. Yes. Xi's are all greater. You will see that she will demand only those chores where her disutility per price is minimized, where her pain per dollar earned is minimized. Right? Okay. So from this, and on top of that, we will need, so this is the optimal bundle characterization, particularly this. Demand only those chores that minimizes the disutility per dollar earned. And demand should be equal supply. Yeah, this is just the feasibility constraint. So now let me tell you the characterization of BMS file. So whenever I say X feasible, I mean that the demand equals supply. So I'm going to force that. Okay, now I'm going to try and compute. So now what is my goal? My goal is to find such prices and such allocation. Prices, once you announce these prices, the allocation that we choose should be an optimal bundle for every agent. and demand should be equal supply. So my goal now as a centralized authority is compute such price and allocation. Okay, we can debate about why centralized, this is the market, blah, blah. But right now, from a computer scientist, a theoretical computer scientist, this is my goal. Okay. So when I say X feasible, I mean that these set of constraints are satisfied. Non-negativity and total unit allocation, total allocated is 1. I am doing badly at time. I have like 20 minutes left.
25 more than that. Yeah.
Okay. So BMSY said that look at again the Nash welfare objective, product of these utilities. Okay. Now you don't want to maximize this utility, you want to minimize them, right? So you minimize that subject to X being feasible. Okay. Why did they come up with this? Okay, so first of all, this does not make sense at all. Like this formulation, minimizing product of disutility subject to feasibility constraint is bogus, I would say. There's a trivial solution. Zero. Right? You choose one of the agents, your favorite, don't give them anything. The disutility is going to be 0, product is going to be 0 no matter what you give to the others. Yeah. So they said, okay, these are bogus solutions. We want to just avoid the bogus solutions. So open constraint. Okay. And minimizing or maximizing product is same as just apply log. Log is a increasing increasing function, so it's the same thing. Yeah. Now this.
So there is still no constraint on how small I can make DI of it.
Yes, no constraint on how small you can, but it has to be a local optima. What does the local optima mean? That around that point there is a neighborhood, however small, okay, but there is a neighborhood in which there is no better point.
Okay.
That's the catch.
Okay.
And this resembles highly to the goods convex program from the 1959. Okay, actually that probably was the motivation for looking at this formulation. For goods, we already know that this program works perfectly fine, and it is a convex program now because you are maximizing a concave function. Log is a concave function. Vi is, let's say, linear. Log of a linear is concave. So maximizing a concave function is perfectly fine. It's a convex program, right? And local optima is going to be global optima. Everything nice, right? And this is heavily used in the algorithms as well. So everything is nice. This is a non-convex program. You are minimizing a concave function.
But now you want only the local optima in the interior.
You only want the local optima. That's the catch.
Because otherwise,
You will not.
go to the boundary.
Yeah, exactly. Otherwise, you'll go to the boundary.
But you didn't know.
Global optima are at the boundary of the tool.
You
Yes.
didn't know that a local, I guess, maximum for the exist that is not on the boundary.
Good. Yes, it is known. And that was one of the important result of being as well.
So you mean on the left?
For the goods, no, there is a convex.
So what they prove is that look at the feasible region.
You need
Project-
minimum.
Yeah.
It's a concave.
Okay. Yeah. Oh.
So what they prove is that look at the feasible region, project it to this utility space. It will be still a convex region. Look at the minimum Pareto frontier, right? It will look like something like that. Look at the minimum Pareto frontier where there is no better allocation in terms of pain or disutility. Yeah, on this minimum Pareto frontier, non-convex set, right? This Pareto frontier is a non-convex set. On that, whichever point maximizes the product of the disutilities, that is going to be a local optima of this tool. So there exists one question. Okay. And there might be many. And this was one of the reasons because we are after local optima. There can be many of a non-convex. Okay. Yeah, so the problem is that it's a non-convex program. Other thing is that open constraint, but the saving grace is that we are only after local optima. Okay. I would like to give you a geometric view because we will use it heavily. What does a local optima mean? So look at the lower Pareto frontier. Again, because you are minimizing the sum of the logs, you will always, and now let's project the feasible region to the distributed space. Okay, so it will look something like this. And your local optima will be on the lower Pareto frontier. Wherever you look at the gradient of the objective, so log di is just 1 over di. The gradient is just 1 over di. At the local optima, the normal to the supporting hyperplane had to be proportional to the gradient. Basically, it is saying that when you try to minimize this objective, at this point, that means you will go opposite to the gradient. Then you go out of the feasible region. So within the feasible region, there is small, whatever small, but there is a neighborhood where there is no better point. Yeah, but geometrically, there is a supporting hyperplane whose normal is proportional to the gradient. Okay, I had a quick proof of why this gives CEI, but I think I will skip it. Okay, it'll be there in the slide. The only thing I would want to mention is that if we are after FPTASs, so approximation, yeah. So we'll just say that the gradient, the characterization will be that the normal is approximately equivalent to the gradient up to multiplicative 1 plus minus epsilon. And in terms of market, it will translate to prices where everybody buys optimal bundle, but their budgets are 1 plus or minus epsilon. Such an allocation. Okay. So a little bit of unfairness, but just little bit. Okay. So you're after local optimized, you said, kind of or hinted that what's the big deal? Apply gradients, right? And that to an approximate KKT point. So, right? And that's what we thought initially. And we tried. We were not able to prove any type of convergence. Then we thought, okay, let's see what is wrong with the gradient, kind of any type of gradient is mirror different, blah, blah, blah. We did a lot of experiments, everything. What's your guess here? What happens when you apply gradient descent from the inside of the feasible region? So you want to minimize this objective. So you want to move in the negative of the gradient. This is the gradient, right? What happens? Look at the minimum DI value. That will have maximum 1 over DI value, and that will decrease the fastest.
The attractor is at the boundary.
The boundary that you are trying to avoid. Yeah. And we thought, okay, let's try to avoid this boundary log barrier, blah, 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 but you already have a log in the objective. So you can't even apply the log barrier. You can't do kind of interior point type of method that you force yourself to be in the interior order. Yeah. I mean, we couldn't do it. If you can think of something, that would be great. Okay. No matter what we tried, experimentally we saw that it always go to that boundary that we are trying to avoid, where some DI becomes 0. And other thing we noticed was that there are other local optima, right, which are the final solutions, but they are unstable in the sense that there is a very small neighborhood where they are fine. As in the small neighborhood, if you apply gradient descent, it will go to this. But if you go outside that small neighborhood, it will go to these zero boundaries. Okay, so they are unstable local optima. So then what do? So we say, okay, let's flip the problem. We know that it's very nice to maximize the product because maximizing is a concave function. It's a convex program. But from inside of this region, it's a minimization. But if you look at in the positive quadrant below the lower curve, from here you can try and maximize. Now this is a non-convex region, but still you can define local optima the way I defined in the geometric sense. You want to find, so now this is a non-convex region, which is below the lower hull of your distributed space. Okay? I want to find a point in that where normal to the supporting hyperplane is proportional to the gradient. Same definition.
So is it the case that you're now working with a good function with the bad domain?
Correct. So I'm thinking of this is a bads domain, and flipping it, this is a goods domain is how I'm thinking. Okay? And I'm going to force myself to remain below, because otherwise if I try to maximize everywhere outside of this, then you go to infinity. So I don't want to go there. So I'm going to use this lower hull as a bounding region.
I'm sorry, I mentioned a different sense. So I mean, when you could either have try to minimize a convex function in a non-convex set, or maybe you could have a function which is going the other way, but have a nice convex set. So is that what's going on here? Like you're trading the difficulty of the domain with the difficulty of the function?
Yes, that is what I'm doing. I don't know the answer to the previous thing, but I'm trading the difficulty of convex region, with the difficulty of a function. Yes.
So you now need to do a like a maximization where you somehow need to stay inside this exterior region completely, right?
Yes. Never go inside.
Okay.
Yes. But at least I have convinced you that it suffices to find a local maximum point of the product of the distributed in the exterior region, the way I defined. Yeah.
Sorry, how does that help you to find a point in the interior region?
Because the local optima from the interior and the exterior are going to have the same property, that the normal to the supporting hyperplane is proportional to the gradient. That's why I wanted to emphasize on that geometric interpretations. So from the exterior, it's nice. The smallest area is going to increase the most. Right? And that's what we wanted, right? The issue is the obvious ones, non-convex region, right? How to define, we can define the exterior properly only in the distributed space. In the allocation space, it's a lower dimensional thing, right? You have summation of some equalities in the excited space. Supply equals demand, right? So it's not even possible to define an exterior region when you have polytope lies on the lower dimensional, in a lower dimension. What should be the potential function? We want path convergence, blah, blah, blah. So we want all of these. So let's first focus on what should be the potential function. The obvious one is the one that we are trying to achieve, the sum of the logs. So let's say, can we design some kind of method where this potential is monotonically increased? So let's say we start from some exterior region. What would we do? Suppose we project this point to the boundary of the feasible region, the lower boundary of the feasible region. Now this is counterintuitive, but suppose we do that because we really want to remain in the exterior region. But believe me, we'll only touch the boundary, we'll not go inside. Okay. The first lemma we prove is that when you do this projection, because of the properties of the distributed space, this point is going to be coordinate wise better than this point. So greater than or equals. So that means this objective is not decreasing at least. Right? Now what do? We had the boundary, we wanted to remain in the exterior. So we check the condition that we are after. Whether at this point, if you draw the supporting hyperplane, is the normal proportional to the gradient? If not, what can we say?
Move back to the exterior region.
Exactly. So that means if you try to maximize this objective on this hyperplane itself, this is not optimal. There's some other direction where it's better. So you do that, and you will definitely go to a better point. You maximize this sum log objective But now on this hyperplane, yeah, if this point was the rest on this hyperplane, then you would have that normal is proportional to the gradient. But that is not the true, right? That's where you started, right? So you maximize, you go to another point, and for sure, because of the property of the supporting hyperplane, it will be in the exterior region again. Because the supporting hyperplane touches this only at this point or at the boundary. Yeah, and that's all, actually. So from here, you know that you strictly improve the objective. By how much? That we have to argue. But you have strictly improved. Yeah. And you can repeat the same steps. Project. So that's it. That's the algorithm. Start somewhere, some exterior point. Project. Is it a solution? No. Then you go to the on this hyperplane, the maximum point. Now that has to be an exterior point, and then repeat. Okay. Now it's not at all clear that this procedure is really going towards a solution, because your improvement in the objective could be like very, very, very small, right? Like geometrically smaller and smaller, 1/2, 1/4, 1/2. You will never reach anywhere, actually. Yeah. So we have to kind of argue somehow that in every step, if you are not at an approximate equilibrium or approximate KKD point, then you must have a good improvement in your objective. And then that's it. Okay. And okay. So yeah, so I kind of try to convince you about these two things. Yeah, I didn't give you the proof of the first one. And finally, we want this now, that either we are at an approximate KKD point. If we are not at an approximate KKD point, we have an improvement in the potential by at least so much. So let me give you an intuition for why this is true. So if you are not at an approximate KKD point, that means the normal is not proportional to approximate gradient. In the market sense, when you try to translate into, you can kind of convert this normal using that to convert to prices and allocation. You will see that agents are consuming their best bundles, but the amount of earning are far away from 1 plus or minus 1. So their earnings are very, very imbalanced. Okay. Now, if you look at the product objective, it is maximized when things are balanced. Right? If I tell you maximize A times B, where A plus B is 4. 2 and 2. Right? So the product objective automatically tries to balance everything up as much as possible. Although this is more subtle than that, because the valuation functions are different and everything. Yeah, but automatically it tries to balance out, and that basically we utilize that if the budgets, the earnings are very far away, even if they are taking their optimal bundle, you can try and balance them out to improve the objective. So when you try to balance out the budget, the decisions will be balanced, okay, and that will take you to another point here, but the objective would have been improved. Okay, so this is a very high level proof, but that's what we really get, and that's why we get a termination in. So the important part is this 1 over epsilon square here that we want to get rid of, basically. Okay, so ideally we want log in 1 over epsilon, then we can definitely get a polynomial time exact algorithm. We know how to do a final rounding. If the epsilon error is inverse exponential, okay, but the point is to get inverse exponential error, in polynomial time. So log 1 over epsilon. So that's the main open question. How much time do I have?
10 minutes. 10 minutes.
Okay, so these are in the same paper, we have extension to one homogeneous and everything. Now, when we talk about general one homogeneous function, no explicit representation, it has to be through the oracle access. Yeah. And then everything, all these projection of the feasible space to distributive space, working with the distributive space, coming back and forth between checking feasibility or infeasibility of the point, you have to go back and forth between this utility and allocation. In the linear, it's everything is LP, nice, fine. With general valuation, it becomes a convex program. Everywhere you incur error. The point was, is it the case that the errors blow up or can we contain them? Immediately, it's not clear. You can contain them, but with some more technical work, we can contain them, and that was actually main part. The algorithm is very simple. Even the analysis for linear is not too hard. The main crux was to kind of extend it to, like, that's where all the math goes. But it goes through finally. But the main idea is what we have for linear, it works for the general case. Also, budgeted version you can do. Now your earning requirements are different. You need to earn, let's say, $2, I need to earn $10. Still everything would work. Only the objective will get weighted. So BI is the earning requirement for agent I, then you want to maximize summation I, BI log BI. Or minimize. Okay, so everything will work out. And okay, so and we can also extend it to mixed manner. As I said before, you have to first figure out whether it's a goods heavy instance, beds heavy instance, or neutral instance. In the neutral instance, there's a feasibility problem. In the goods heavy instance, you treat it as a goods problem. In the beds heavy instance, you have to treat it as a bads problem. And so in this case, we can show that the feasibility polytope is not so nice now. It's not, doesn't only lie in the positive orthant. It may be intersecting with the other orthants. But still you can define this exterior region here below in the positive orthant, below the lower curve, and everything. Okay, so one concrete problem is that
in the same, so if you run the same old algorithm, what happens if you leave the positive orthant? I mean, or will that not happen?
No, we don't let.
Or you just cap out at the axis?
Yeah, you cap out at the axis.
Okay.
So remember, you're maximizing the product. So when you look at the supporting hyperplane, you will never go.
That's it. Yeah, okay.
But that's a very good point. Yes. Why would you go? Yeah. Is that question clear? Like what? I missed that point in the previous explanation, but that's a very important point, that why the maximizer doesn't go out of the positive order. Yes. Okay. So we were stuck with this convex, non-convex program with open constraint for a long time. And we couldn't see a way out. And then we were talking about something else with Christian. He had worked on some infinite goods and so on. We were talking about it. And then he mentioned this dual of the Eisenberg-Gale program. So let me just recall again that this is the program we looked at, minimizing the product very strictly, subject to distributivity being strictly greater than 0. And we are only after local optima. With the budgets, it's just the weighted version. Now, for Eisenberg-Gale, there are many convex programs, and basically they are duals of this. So you take a dual of this, then again take a dual of that, and there's a systematic way of taking duals of convex programs, and so on, and you get different programs. And one of them, the direct dual of this is this. Now, this is in the allocation space, this is in the price and the band per buck, or the pain per buck space. Okay? So the PJ is the price of item J, or good J in this case, because it's for the goods. And Vij, 1 over beta I, if you swap PJ and beta I, then 1 over beta I captures the utility per dollar here. We can mimic this, say, like we mimicked here. Right? Instead of minimizing, use the max there. Again, everything works out. You just flip the sign because in the goods case, you want to consume where value per dollar is the maximum. In the chores case, you want to consume where pain per dollar is the minimum. So you flip the sign and flip min to max. Everything works out again, except for one issue. Again, it's the same thing. Log beta I So you are maximizing minus of log beta. That means you are minimizing the log beta. So you should set beta is to 0, pj is to 0, and you have infinity. The same, again the same boundary issue. Yeah. And pictorially, this is Christian's slide. This is how, like for a small thing, it looks like for these constraints, right? So there are these boundary points that are useless, basically, where you have like zeros. Okay. Now, recall that we can prove that when you take the KKT points of this, if the KKT point also has Pj and beta is greater than 0, then we can prove that these correspond to the computative. Now recall that at competitive equilibrium, every agent is earning exactly their budget, right? And supply equals demand. What does that mean? What is the total price be? The total price will be the total budget, right? So it's a redundant constraint in that sense. It's automatically satisfied at the KKT point. So we said, what if we put that constraint explicitly? Okay. And let's also assume that all the DIJs are non-zero. If somebody says that I have 0 pain for doing some chore, I'm going to happily give that chore to that person. You have 0 pain, why do you care? Right? So let's say all the dispute-free values are non-zero, and I put this constraint. What does this force? This force is that at least for some chore, the price has to be positive. If for some chore the price is positive, that forces all the betas to be positive. And that will force all the prices to be positive at the KKT. Just once constraint, it solves the problem. Now we are really in a proper non-convex program, and we want to find a local optima. This is really a non-convex but local optimization problem. Pure. Okay. Can we solve it in polynomial type? That's the question. Again, so basically pictorially it looked like this was a feasible region. We cut it. And in cutting is such that it covers all the bad boundaries. Okay. And the algorithm we design is a full Frankfurt style. What does that mean? We start with some feasible point. Now we are in the going to be playing with a feasible region. Okay. And look at the gradient. Okay. The gradient is going to be, so in this program, when I impose this condition, the first part makes no sense. That's a constant. Right? So I can get rid of that first part and think of just finding maximum of the sum of, again, just pi log beta. The sum log object. Right? Minus of, or minimizing that sum log object. So the Frankfurt does this. Start with any feasible point. Take the gradient of this. Okay. Now think of solving an LP with that gradient being the cost vector. You will hit another feasible point, and you can kind of prove that because you kind of moved in the gradient direction, you will improve the objective. How fast? That's the question. That depends on the program and the objective function and the constraints. But that's it. You will keep doing this. This is automatically gives you a potential function, everything for free. It's a known method, right? The main point is the convergence, and still we can show that it converges. And yeah, I should have, yeah, finally we had like n over epsilon conversion. Okay, so we improved one factor in the epsilon, but yeah, still not the log. And the dependence on the budget is not nice. Right, so it's not log of BIs, but it's a BIs. Okay, so the main question I would pose here and just ask is that now we have a non-convex program, proper non-convex program, and we are after local optima. can we do something with interior point method, ellipsoid, anything? To find epsilon approximate solution in log 1 or epsilon time, polylog. Just quickly, let me just say that what's the complexity? So the slight generalization of the market, which Aerodegru proves existence for, which is called exchange. So now we are not going somewhere to consume chores or do chores by chores. But it's like you have some chores, I have some chores, we exchange. Okay, but the exchange is also again based on the prices. And this is a barter system. This is how people thought about the markets in the old days, and that's where I think all the wall rush and everybody started. So typically in economics, if you see market, it's typically exchange market. Okay, and so it's completely makes sense to ask the question for exchange, and we say that when you allow some the IJs to be infinity, saying that this agent can never do this chore at all. Okay, this kind of saying that I can teach algorithms course, but if you ask me to teach music course in the next semester, probably I'll have to say bye-bye, I cannot, right? It's like that, right? Not everybody can do every chore, but if you allow that, then for the exchange, we would show that it's really hard. Even with the linear, while for the goods case, there are strongly polynomial time algorithms. So the contrast is stark. And so some people still believe that maybe even for the Fisher, the problem is the exact is hard. Not all the way to PPAD hard, but maybe CLS hard, there are subclasses of PPAD and so on. I think there should be interior point or some kind of method. There's a lot of structure now. So that's the main open question I want to pose to you. And hopefully I kind of convinced you that this is an important problem and mathematically as well as practically and also interesting. Okay, and there are many other questions related to game theory and so on, like what if people don't report their two valuation functions, what happens? What if we want to find not a central algorithm, but more distributed algorithm to reach an equilibrium? The dynamics and so on, and application to fair division. Okay, thank you.
Yes, ideas on how to solve these open problems. So the 1 epsilon, like, is it an intrinsic property of Frankfurt for other Frankfurt type algorithms on, I mean, like similar kind of things where you.
So Frankfurt basically says that this method is going to converge, but how fast?
It doesn't.
Yeah. I mean, there are some general theorems, but we couldn't kind of quite apply them, and you need some nice properties about the objective function and so on. And so we proved it, our own theorem. This is more general than this application, Yeah. Basically, any if you have some objective and any feasible constraint, we did some analysis to prove convergence.
But do you think they're adding the system?
No,
Okay.
we don't have a counterexample. We are nowhere near the counter. That's why I believe that there might be interior point method.
The exterior point method that you are considering it is always in a star-shaped set. That is all the points are visible from the origin, for example.
Yeah. Because it's a feasible discrete space, right? So the boundary, the minimum Pareto frontier is going to be visible from the origin.
Because there are some sampling the non-convex but star-shaped domains. I'm wondering whether one could consider a randomized algorithm.
Sure. Yeah. Even randomized algorithms. Yes. Even putting in RP would be.
Okay, that's time. Okay, now. Talk to me for a bit.